Welcome, class. So, we did not have a Zoom session today on Wednesday the 27th. We are not having a Zoom session today on Wednesday the 27th. We're going to be watching this video instead. So, as I look here, I'm going to go into this unit 2 charge. As I look at this unit 2 charge, there's a charge question number 2. Please make sure you address this question. Addressing this question is where you're going to say, what is the net charge on S and R? After you address that question, I'm going to go back to our sticky tape lab. From our sticky tape lab, this is where we're going to get the second half of the laboratory experiment. If you already have part 1 of the lab, we did that yesterday. Today we're going to get to part 2. So what you got to do is you got to analyze the data. So get to this video of analyzing your data, and then after you do that, you're going to make a copy of your Google drawing. So what you're doing is you're watching that video to analyze that data. After you analyze that data, this is where we're going to look at how the tape and other materials interacted. So we see that the top tape and the foil, there was an attraction. So I label here with the forces that the force arrow and this force arrow, they're moving towards one another. There's an attractive force between the top tape and the foil. We also saw an interaction of the bottom tape and the paper where there was both an attractive force. So I'm labeling here with this arrow and this arrow. Now all I did was I dragged the arrows from my label section, and after I dragged the arrows from my label section, I was able to move the arrows from my label section, and then I was able to place them at different locations around. And after I labeled the forces, because I saw that there's an attractive force between the bottom tape and the paper, the top tape and the top tape, I saw a bigger force. So I had to say that there is this force here, and we can indicate that this force is bigger by making a bigger arrow. And so all I'm doing here is I'm making a bigger arrow on both of them. I'm trying to make it so that way both these arrows are about the same size, because I did see a stronger force between the top tape and the top tape, but they were repelling one another. So this was a repulsive force. The top tape and the bottom tape was also a strong force, where that was a big attractive force. So I'm going to make it so that way these arrows are longer than the others, because I did see that those forces were bigger than the others. So I'm trying to indicate that. And I also saw a similar interaction with the bottom tape and the bottom tape, where there was a big force between them. And so that's why I chose to drag these guys from the stronger force for repelling one another. Then, after I also saw in my observations that the PVC rod, which was negatively charged, a negative charge attracted a top tape. So that top tape has to be opposite of that negative charge. So then I labeled all my top tapes with this positive. And then I saw with the PVC rod that the negative charge was repelling the bottom tape. So I know opposites attract, and like charges attract, opposite charges repel. So a negative push away from other negative. A positive go to another negative. A positive push away from another positive. So after we have our document fully labeled, I'm not assigning any charge on the foil. I'm not assigning any charge on the paper, because, well, there was no net charge on them. We're going to get into the analysis of our foil and paper in just a moment. But now we're going to download this, and we're going to download this as the form of a ping, and then we're going to upload it into our document. So I'm going to download. So by clicking the word file and the word download, I'm going to click on the PNG image, and then it downloads this here on my computer. Now for yourself, this might go into your downloads folder. I'm going to move this to a different location. I could move this to my Google Drive if I wanted to. I could move this to some other places. I'm just going to move it to my, I'm just going to have it here in my downloads. And this is my copy of Sticky Data 1. So you can move it around if you wish, but I just have it in my downloads. So then I'm going to come back over here to my sticky tape, and I want to insert that image. So I'm going to insert the image, and I'm going to upload it from my computer. Now, where I put that image was in my downloads, so I need to make sure I go to my downloads. And I want the one I had, which was my copy of Sticky Data 1. And I can verify in the image here that this is the one I desire. I open this up, and now my file has my Google drawing in it. So after I get to that, now I'm going to be getting to my analysis. So what I'm going to do is I need to click here to see the image. And after I click there, I see I have to insert a hand drawing for number 1, insert a hand drawing for number 2, and insert a hand drawing for number 3. So I'm going to click here to see the image. And this is what's going to pop up. So we're going to have to recreate a model trying to address the questions where we're going to draw the images here for number 1, number 2, and then furthering to number 3. So we're going to draw and apply these images onto here. So I will first take us to viewing how we're going to draw up number 1. So as we look at number 1, we have here a top tape and a bottom tape. And I'm also going to remind us of the data we had here, where we had the top tape as this positive and the bottom tape as this negative. So we kind of already assigned the tape, but now we're going to use this analysis here to get to what it is that we're saying. That how did this top tape and bottom tape get a top tape positive, bottom tape negative? So in our drawings, this is what we're going to be drawing up. So we do know that this top tape has a positive charge, positive charge, positive charge, positive charge. We know that the bottom tape has a negative charge. So 1, 2, 3, 4. I'm keeping it equal. I have 4 on top, 4 on bottom. If I make a positive on top, I make a negative on bottom. Because we set the net charge of this entire tape to be 0 when we neutralized it. Before they split though, we had here a positive, negative, positive and negative, positive and negative, positive and negative, positive and negative, to where they were close to one another, near one another. If we were to even zoom in on this, we would see that there's a positive over here and there's a negative over here. That next to that positive would be another negative. But really what we're talking about here is this net charge. So we don't need to draw in all the positives and all the negatives that could occur on this, because then we're getting in, well, to a really big drawing. And really we're just trying to think about this net charge, where there was more positively charged and more negatively charged on both of these pieces of tapes. And all that happened was this bottom tape took the electrons from this top tape. So we could even assign it to where this negative goes in between the two pieces of tape. We could draw it like that. I'm going to draw it to where it's a little bit easier to see visually, and we can then just have it to where there's a positive and a negative. But when they're connected like this, this charge is associated to this positive, and this negative is associated to that positive. When we separate the two, now we have a positive up top and a negative down below. So this would be good for an analysis here for number 1. I would then take a picture of this and insert this picture as my hand drawing. As I continue, I'm going to take a look at number 2. We saw in our observations for number 2 that the top tape and paper showed this attraction. We already know that this top tape has this positive charge distribution on it. We also already know that the bottom tape has this negative charge distribution on it. So we just have to create some kind of model to explain why the paper was attracted to the top tape. The paper has a net charge. I've never gotten shocked while picking up a piece of paper. I've never felt static electricity. There is no static charge to this paper. But what happens is within this singular atom, if I were to just draw an atom off to the side and make it separated from everything, I could draw in just a singular atom. And as I draw in a singular atom, I'm going to draw in the electron cloud and put the positive charge in it. So this positive charge is within the border of the atom where this circle really is a cloud of electrons. So what we're seeing happen here in this atom is that this top tape kind of repels a little bit of this nucleus, the positive charge. It kind of repels the positive charge within it, bringing or allowing more of this electron cloud to form closer to one side. What we're doing here is polarizing the atom itself, making it so that way there's more charge on one side of it than on the other. And it would follow a trend going up into the paper. But the strongest of this polarization would occur where the two objects are closest to one another. So this top tape is really close to the paper. So this positive charge has a big repulsion on the positive charge in the atom of this paper. The positive charge has a big attraction on the electron in the atom of this paper. Now, in paper, electrons are not free to move. They don't jump from atom to atom to atom and move around. And that has to do with the atomic structure and the material that is going on here in this paper. We're not going to dive too deep into that, but we just got to recognize that these electrons, yes, they're in this cloud, but this cloud is stuck here. It's static electricity. So we see that this charge distribution, this polarization occurs in the paper. It's going to be sort of similar with the bottom tape, where this negative charge and the bottom tape is going to be attracting to the positive charge in the atom and deflecting, repelling some of the electron cloud to the other side, making it so that way, in general, the electron is going to be on the other side of this atom. And it's going to happen similarly to all the atoms in this paper. But just like how with the top tape, the strongest distribution, the strongest polarization will occur where the charges are closest to one another. So I tried to draw that the electron cloud is thicker on the right-hand side than it is on the left-hand side. And this positive charge that is associated to the atom is closer to the left-hand side, closer to this negative charge here, the tape. Now this is good because paper does not allow for conduction. But if any of you were to stick aluminum foil into an outlet, don't do it. Aluminum foil has electrons that are free. That means, unlike with this paper, this electron that's in this cloud, which is stuck to this atom, an electron in foil is freer to move. It's not completely free, but it's freer to move than it is in paper. So the top tape has the same distribution. So we saw that this top tape has to have this positive charge based on the PVC observations. And this foil, we're going to create now a model for this foil where we're going to have an atom that's going to have a positive charge and a negative charge. They're associated to one another, but this negative charge is free to move. This positive charge is going to be the one that's more stuck. We're going to associate this positive charge to the proton in that nucleus, but really we're just going to kind of say that this positive charge is going to be associated to that atom. And so what's going to happen in this foil, if we were to just look at the foil itself without anything, so I'm going to draw the foil without anything, without any charge, without any tape brought up to it. The way the foil looks is I get a positive and a negative. And then close to that positive is another negative. And then I get a positive and a negative and a negative and a positive. Now this is how it looks without any charges brought near it. But what happens here, this positive charge attracts a negative charge and repels a positive charge. So what we're going to do is take all these electrons that are up here. They're free to move about, so they're going to travel down this foil, making it so that way there's going to be more of a negative charge down at the bottom end of this foil, leaving an equal positive charge up to the top. Now I could continue drawing in the positive and negative, and how they alternate throughout, but I'm just really trying to draw in the net charge. What we're doing is we're polarizing the entire material, not just a single atom, but we're polarizing the entire material, where now we have more negative charges and more positive charges. And we did this without touching anything. So this tape and the foil, they're not touching, but we still see this reaction. So then we can get to the bottom tape. The bottom tape has a negative charge distribution on it. We're going to see a similar reaction where the negative charges in this foil will be repelled by this bottom tape, moving the negative charges up to the top. The negative charges, the electrons, are the charge carriers. So those charges move, leaving the positive charges to stay behind. The charge carriers, the electrons, are the ones that are able to move. So this negative charge here repels the negative charges in this material, now polarizing it. So the foil is definitely different than the paper just in how this distribution works. So I take a picture for my number 2, I insert this picture to number 2, and I take a picture for number 3, and I insert that picture to number 3. So I insert my picture here, I insert my picture here, I insert my picture here. Now I have to answer my guiding question. Is there a force between two pieces of tape that are not touching? Yes. There could be a force. Now this is trying to answer this in general. So evidence. So I saw some evidence. One piece of evidence I could say, well, top tape and top tape. Repelled one another. Bottom tape and bottom tape repelled one another as well. I'm lazy and I'm trying to copy and paste. So top tape and top tape repelled one another. Bottom tape and bottom tape repelled one another. We also saw that the top tape and bottom tape attracted one another. And so with this evidence, you can then try to, well, tie in some of your reasoning. A lot of you already have the idea that opposites attract. Top and bottom, they were opposite from one another. Or rather, they attracted one another, therefore they have to be opposite from one another. So what you see is this attraction. That's what you see, that's your evidence. Your reasoning is, well, I know that when things attract, in terms of charges, they have to be opposite from one another. And if they're the same charge, that means they repel one another. And so you're seeing that here in your observations. So all you have to do is just point out your reasoning, tie in some of your prior knowledge as to what that is and how these two tapes repel and attract one another. So once you get done answering this guiding question, go ahead and turn in your assignment into the Schoology page. You can use this how to turn in the assignment video. And also please make sure that you get this charge question number 2 when we're looking at this net charge on S and R. When we have this negative rod here, we see that sphere S is attracted to and sphere R is repelled from. Once you get done with this, please turn it all in. Thank you very much.